Hello, and welcome to this video on how to create an open-source router using a Raspberry Pi. There are many videos and posts on the internet on why one can't or shouldn't use the Raspberry Pi as a router. But I'm going to show you an implementation I've been using as my home router setup. Best part is, we will be using only the Raspberry OS and common Linux packages, and we will not have to write even one line of IP tables or NF tables rule. By the end of this video, you'll have a fully functional Raspberry Pi router, ready to take control of your network. So, grab your Pi, buckle up, and let's get routing. To build our router, we're going to need a few things. 1. A Raspberry Pi or any computer with a modern Linux OS such as Debian, Fedora, Arch, etc. For this setup, I'm using a Raspberry Pi 5 with the GeekPi NVMe hat. One of the disadvantages of using a Raspberry Pi is that it only has one Ethernet network interface. In my setup, I'm adding an ASUS 2.5 gigabit USB 3.0 Ethernet NIC. Ideally, you want to use a PCIe network card as it's supposed to be more reliable, but this setup works fine for a home setup since this is mostly for fun and not for profit. Finally, while this is not absolutely required for this tutorial, we will also need a switch or an access point to connect multiple computers to our router. This router setup can be used to give internet to, and man-in-the-middle any computer to give you visibility into all the network activity to, and from any network device. In my case, I'm using a TP-Link AC1200 which doubles as a wireless access point and as a switch. So here are the general steps of how we'll go about setting up our router. I'm going to include all the steps in the comments below, so that it will be easy to follow along. First, we will install the required packages. Second, we will configure the resolution and hostname. Third, we will configure some nice-to-have settings on NetworkManager service config. Fourth, we will configure firewalld. Fifth, we'll configure our network connections. Sixth, we will configure dnsmasq. Seventh, we'll set up the dnsmasq service. Eighth, we'll configure the logging connections that have been happening on the machine using rsyslog service. And finally, anytime you log something, it's good to have log rotation set up so that you don't fill up your disk and bring down your router or machine. I won't go into details on how to install a Raspberry Pi. There are many great videos here on YouTube on how to get started. Here, as you can see, the installation is starting. I'd recommend to connect the Pi to the internet so as to get updates during installation. As you can see, an IP has been assigned. I'm going to select the defaults for my location. Feel free to change these settings to match your location. I'm going to enter my username and password. We only need one user for this router setup. I will be using RTR admin user and set my password and select Next. We will not be using the onboard Wi-Fi, so we'll skip. Firefox is my preferred browser, so I'll select it. Feel free to select either browser. We won't be using the Raspberry Pi Connect, so I won't enable it. Select Next. Since we're connected to the network, we'll go ahead and update the Pi, so we select Next. And as you can see, the update is complete. I'm going to go ahead and restart the Raspberry Pi. When the Pi comes up, I'm going to change the default resolution here to make it easier to see. Before we start configuring our router, we'll need to install the packages that we require for our router setup. We only need to install firewalld and rsyslog package. This installation already comes with the dnsmasq base package. We don't need the full dnsmasq package. The Pi uses NetworkManager and logrotate, so we don't need to install those packages. Other Linux operating systems, or probably even the minimal Raspberry Pi image, might not have those required packages in their base installations. Install them before proceeding. Next, we will set the hostname using the hostname control command and modify the etc file to match the new hostname. Fedora and other related OSs such as Red Hat, Alma, and Rocky Linux have a package known as NetworkManager config server. As it notes, it adds a NetworkManager configuration file to make it behave more like the old network service. In particular, it stops NetworkManager from automatically running DHCP on unconfigured Ethernet devices and allows connections with static IP addresses to be brought up even on Ethernet devices with no carrier. No carrier is just a fancy term to mean that no signal is detected on the interface, either from a missing or broken cable. Auto DHCP is a nice-to-have feature on a PC. It's what gave the Pi a connection on first boot, but it could lead to inadvertent connections on your server. Even when using DHCP, as we'll do later in the video, it's advisable to make that setting explicit per interface. I'm going to remove the comments from this 00server.conf file, add it to the Pi, and reboot. When the Pi comes back up, you'll note we no longer have an IP configured through DHCP because of the no auto default setting. Next, we'll be configuring firewalld, which is the star of our router. It is the NF tables frontend, and it provides a dynamically managed firewall with support for network/firewall zones that define the trust level of network connections or interfaces. Firewalld has really matured from early days where it received a lot of criticism from old Linux faithfuls. I won't delve too deep into its use cases. If you're interested, leave a comment below, and I can make a separate video going into details. For our use case, all we have to know is that we will be using two zones, an external and an internal one. The external zone will connect to the wide area network, or ISP connection. The internal zone will be connected to our local area network, or PC. It could also be connected to an access point or a switch to give internet access to many computers on your local area network. To allow for traffic from the internal to the external zones, we will need to configure a policy to allow ISP traffic originating from the homeland zone to the isp-conn zone. Generally, like the documentation notes, all the zone configuration will distill to the following principles. 1. Traffic ingress is one and only one zone. 2. Traffic egress is one and only one zone. 3. A zone defines a level of trust. 4. Intrazone traffic within the same zone is not allowed by default, as we'll see below. This documentation is incorrect. 5. Interzone traffic, zone to zone, is denied by default. Principle 4 and 5 are actually a consequence of Principle 3. Principle 4 is configurable via zone option -- remove forward. Principle 5 is configurable by adding new policies like we'll need to do for our router. The first zone we'll set up is isp-conn zone, which will be connected to the wide area network. The default level of trust for this zone will be drop, which is set using the target drop. This means any traffic attempting to reach our router through our public WAN IP will be dropped without response. We will also be adding the masquerade option for this zone. The masquerade option is a fancy term to mean source-NAT, or network addressing translation. Source-NAT modifies the source IP address of outgoing packets, typically replacing it with the router's public IP or isp-conn IP, allowing devices in a private network to communicate with external networks. We will reload to enable the permanent config and run the list all command to view our config. As you can see, the config has the target set as drop with masquerade turned on. The next zone we will configure is the homeland zone. The homeland zone will use the reject target, which is a much nicer than the drop target in that it will let the client know, with an ICMP response, that it shouldn't be reaching the port or service and that the network packets are being rejected. We will need to add some services for the homeland zone such as DHCP, DNS, and SSH. We will reload and verify the zone settings. We don't need to have the forward or masquerade option configured for this zone. We will add a new policy to allow traffic from the homeland zone to the isp-conn zone. We will set the default target as accept, which will allow all traffic through. We can also set targets such as reject and drop, but to reach services on the internet such as HTTP and SSH, we will need to add specific services to the policy like we did for home/LAN zone. Let's reload and look at the policy config. As we can see, we have the target set to accept, with home/LAN as the ingress zone and isp-conn as egress zone. And with that, that's all the firewall configuration we need for a router. That was easy, right? Not one line of IP or NF tables rule. Next, we will use the NetworkManager CLI tool to configure our network connections. If you're using a Raspberry Pi, plug in the USB Ethernet adapter. Use ifconfig to check for the network interfaces. As you can see, we have two Ethernet interfaces along with loopback and the Wi-Fi. The onboard interface as ETH0 and the USB interface as ETH1. First, we will configure the ISP connection on the ETH0 interface. With this connection, we will be employing auto DHCP so that the IP is automatically assigned by our ISP or upstream router. We will ignore the DNS provided by the ISP and configure Cloudflare and Google DNS as our default DNSs. We will disable IPv6 and modify the firewall connection to be the firewall-d zone isp-conn that we set up earlier. Next, we will enable the isp-conn connection. The next connection we will set up is the home/LAN connection on ETH1. We will set up the home/LAN IP to 192.168.24.1 with a subnet length of 24. We will modify the method to be manual instead of DHCP and disable IPv6. We'll set up our connection zone to be home/LAN. And finally, we will enable the home/LAN connection. Next, we are going to set up dnsmasq, which will provide DNS and DHCP services to our local area network. Please refer to the dnsmasq man page for full details on all the config options. We're going to create directories for config files and logs. For our router setup, all we have to note is that we are setting up Cloudflare and Google as our DNS servers. We will be listening on the home/LAN connection. The DHCP range will be 192.168.24.52, 192.168.24.254 with a lease time of 2 hours. This gives us about 50 IPs that we can set up as static IPs and 200 addresses available for DHCP. We will also supply a DHCP option to point to our router, which on the DHCP client will be the gateway or the IP that we set for the home/LAN connection. We will also specify a DHCP lease file path. This path will provide us with the list of all DHCP leases and IPs. We will turn on some logging options so we can see the DNS and DHCP activity. Default dnsmasq logging is to the daemon, which will be in journal D. Feel free to comment out these options if you find the logs too verbose. After configuring dnsmasq, we are going to set up a home/LAN dnsmasq service using systemd. We will point to the home/LAN config file that we just set up above and set up some options to always restart the service. If we didn't set up the ignore carrier option in 00server.conf, failure to plug in an Ethernet cable results in ETH1 interface not being enabled, thus causing dnsmasq service not to start. We are going to reload the systemd daemon to load the home/LAN dnsmasq service file. We will enable the service so that it starts at boot. The default login facility for dnsmasq that we configured above is set to daemon, which means that the logs will be sent to journal control. We will use rsyslog to write these logs to some files on disk so that we can be able to use any text editor to view our files. We are going to separate the logs into 2 log files, one for dnsmasq logs and another one for dnsmasq DHCP logs. And finally, we will need to rotate dnsmasq.log and dnsmasq DHCP.log files so that they don't fill up the disk. We will rotate the logs daily. With every log rotation, we will set a date extension, and we will set the logs to be a maximum size of 50 megabytes. We will keep only 14 days or 2 weeks worth of logs. And we will run the post-rotate script to send the hang-up signal to allow for rsyslog to start logging to the newly created log file without restarting the whole service. And with that, you have a fully configured Raspberry Pi router. Let's restart the Pi and start using our brand new router. When the Pi boots up, we will navigate to the dnsmasq logs file folder. I had mentioned you can plug in a PC or router to your ETH1 connection. I already have an AC1200 router that I have set up in access point mode. I will not go into details of how this is set up, please refer to your router manual on how to set it up. All we need is set it to acquire an IP through DHCP mode. You can use any machine that uses DHCP to acquire an IP, such as a laptop or another Pi. We are going to go ahead and tail dnsmasq dhcp.log file. And as you can see, when I plug in my Archer A6 access point, it is assigned the IP 192.168.24.203. You can see that the subnet is set to length 24 or 255.255.255.0, and the gateway is also assigned pointing to our router. When we look at dnsmasq lease file, you will see the Archer A6 lease expire time and epoch time, MAC address, IP, hostname, and client ID listed. We are going to look at dnsmasq.log file to see all the DNS queries. As you can see, there are queries to Amazon, Wikipedia, and also tp-linkcloud.com. Also, you can see, first queries to Amazon are forwarded to upstream servers. dnsmasq returns cached values for subsequent queries to Amazon and Wikipedia. This also works for other domains that dnsmasq will query, and in effect it speeds up your internet connection because your DNS queries will not have to make the round trip out to the upstream DNS servers from Cloudflare or Google. I'm going to tail the dnsmasq's dhcp.log file again while I connect my Pixel 6 phone over Wi-Fi through the TP-Link access point. And as you can see, it is assigned an IP of 192.168.24142 over the ETH1 interface. I'm going to tail dnsmasq.log to look at the queries coming from both the router and phone. I'm going to open random apps, and you can see the queries that the phone makes. One benefit I mentioned of having your own router is the ability to man in the middle any network connection that's happening over your network. I'm going to install the TCP dump tool so I can monitor all the network packets going over the ETH1 interface. I'm going to specify ETH1 interface and the lowercase n option to see all the IPs and ports without using their host or port service names. As you can see, this gives you the ability to look at all the network packet information going over your network, which includes IP, ARP requests, ICMP, and more. Earlier, when we looked at dnsmasq queries for the Pixel phone, we were only looking at traffic over port 53. Here you can see messages from all ports, including 443. With TCP dump, we only need to use the -w option to write all the packets to a file on disk for later investigation. One question I had when I set up this router was what the performance would be like of the network. Here I'm going to start TCP dump and start our speed test on my Pixel 6. When I first ran this, I was surprised by the CPU spike, but if you look closely, you can see that the CPU percentage is brought up by the terminal activity. And when I close the terminal, even though the speed test is still running in the background, the CPU utilization goes back to 0. The CPU spike was from the activity on the terminal, and even when maxing out on my 300 megabits per second internet connection, the CPU stays at 0. Last thing to note in this long video is a useful option on firewalld. The option set-log denied all. This will give you visibility into all the denied logs by firewalld. This is very useful for when you're debugging. As you can see, we have some drops on the filter in isp-conn. This makes sense because this inbound traffic is not allowed on that zone or connection. isp-conn in my use case is not connected to the internet. Rather, it's connected to another TP-Link router I use for my home connection. Instead of connecting it to my other router, this is a perfectly valid setup to connect to your ISP or upstream router, and it will block all incoming connections like a secure router should do. And that's all for this video. Thank you for sticking with me. As you saw, the Pi is fully capable of running a router while the CPU is sitting pretty at 0%. It's daring us that it's ready for any mission. Heck, It's fit for 5 missions. What would you be interested in adding to your Pi router? Media host? Open up ports in the isp-conn WAN connection to get access to your home network while on the go. A NAS? WireGuard VPN? How about Pi-hole for ad blocking? TFTP boot to give diskless booting to our home network? Leave a comment below. Thanks.